All right, I thought I'd start this presentation off with a short video clip.
Have you taken any steps to carry out President Trump's plans? He says he wants to annex Canada.
Originally I was planning to come up here and talk for quite a while about Christopher Columbus. But then I asked myself, what exactly is the point that you're trying to make here? So I decided not to beat around the bush and instead come straight to the point. And that point is we need a reason why. Why leave the cradle of Earth? Why venture out into the relative unknown? Why should you care about space infrastructure or space settlement? Why should anyone care? Well, 500 years ago, there was the old world and the new world. Today, wine still comes from the old world or the new world, but for all intents and purposes, the old world has expanded to include the entire solar system and everything in orbit beyond it. We are almost ready to turn our geopolitical attention to the new world. And that would be a good thing, because fear of missing out on the new world might distract some expansionist leaders from engaging in the zero-sum game of geopolitics on Earth. It's really a negative-sum game if you think about it. You see, the value proposition of space settlement starts to be unlocked when expansionist powers start to really believe that other expansionist powers might beat them to the punch, that through inaction they may cede the wealth of the solar system to an adversary. Kennedy said it well in 1961 when he said, "We go to space because whatever mankind must undertake, free men must fully share." Okay, let's pause for a second. I want to give you a quick overview of today's presentation before I go into more depth on each topic. The first section I just did, that's the why of developing transformative space technologies. The reason why is that every little bit of forward progress will have a significant effect on the fear of missing out, and space settlement FOMO will directly affect how much money gets spent and wasted by human civilization on zero-sum geopolitical games. But there's still a problem. The rocket equation makes it way too costly for people to venture beyond Earth's orbit using the kinds of technologies understandable to Wernher von Braun. Now, commercial space interests would prefer us to all believe that this is due to the inherent inefficiency of government-run space programs, but we'll take a closer look at the rate of progress in reducing launch costs, and I'll also share some work that I did on how cost per kilogram scales with delta V. We also need to address an important other question. There have been lots of other proposals for non-rocket launch systems, so why haven't any of them caught on? Lots of people will try to answer this question by starting with the observation that non-rocket launch system X hasn't gained traction, and then attempt to come up with plausible sounding reasons as to why this must be so. What you get from this is lots of plausible sounding reasons, but you end up with kind of a who is the real Slim Shady problem. You don't know which reason is real. For what I think is by far the most promising class of non-rocket launch technologies, which is electromagnetic launch, or EML, more generally known as mass drivers, or ground launch assists, I believe that I've isolated the real reason why they haven't caught on. I'll cover this topic of why I think EML is the most promising alternative to rockets, and all of the wrong reasons why EML won't work for space launch. Now, I did say that I'd also explain the real reason why EML doesn't work for space launch. What I really meant to say was, it's the real reason your grandfather's EML doesn't work for space launch. I believe that today we have architectural solutions to the problem, but that have historically held back EML, or electromagnetic launch. It's fundamentally a power conditioning problem, and I'll try to explain what I mean by that. So after explaining the fatal flaw of earlier EML concepts, I'll need to explain why this class of solutions is no longer fundamentally flawed, specifically how at least one technology called variable pitch screw launch solves the fundamental problems that prevented earlier electromagnetic launch concepts from scaling up to space launch. And after explaining that solution, I'll talk briefly about variant systems for the Moon and Mars. By the way, our next speaker, Chris Salvino, is back here. We'll be talking about helium-3 mining on the Moon, and our speaker after that is Roger Arnold, and he'll be talking about orbital infrastructure for reducing launch costs. Finally, I'll talk a bit more about where you can learn more and how you can pitch in if you're interested. All right, so why am I saying failure to launch here? Well, I'm really talking about humanity leaving the cradle of Earth, or human civilization leaving the cradle of Earth, not just into orbit. We've had rockets for decades, almost a century, in fact, and we still haven't left the cradle. Also, I need to discuss this because some people, such as this person who posted a comment on Stack Exchange, believe that reusable rockets have already solved the problem. Now, NASA published a study earlier this year, in fact, where they used their own private data on how much they're paying for launch to determine a launch cost trend. And what they found was that the costs have been going up by 2.8% annually, even after accounting for inflation. They also stated that they observed no shift in this cost trend after the introduction of a new provider. This is code for SpaceX didn't reduce our launch costs. Nevertheless, lots of people believe that launch costs have been dropping significantly thanks to the commercialization of space and reusability. So why is this exactly? I think it's because lots of people have seen charts like this one, or this one. Now, this orange dotted line here has a slope of 10x in 10 years. That kind of gives you an idea what that looks like. These charts all reference another chart from the Center of Strategic and International Studies. So these creators are really just engaging in what's called circular reporting. This is re-reporting something somebody else has already reported. So this is the chart from the CSIS report that the other articles referenced. If you try to fit a line to this data, you might get a slope of perhaps 10x over 70 years. But these 2 points down at the bottom, this is the Falcon 9 point and the Falcon Heavy point, they're particularly influential when it comes to selecting the best slope for this line. So we need to take a closer look at those data points. So this is data from the SpaceX website. It provides the cost of launch and the payload for various orbits. There's a footnote that tells us that the performance values represent the max capability on the fully expendable vehicle. There's also a price of $69.75 million. It's actually gone up to $65.85 million. And under the price is a note that says up to 5.5 MT to GTO. Now, MT here probably stands for metric tons. Why they're using metric tons here, I don't know, but they're using kilograms everywhere else. Maybe a clue in that. But what this tells us is that it's not the price for the expendable configuration, because the expendable configuration is 8,300 kilograms. So what they're probably doing here is using the standard marketing technique of saying prices as low as, which means that the $69.75 million is the price of the lowest cost configuration, not the expendable configuration. But the bottom line is that you can't get the cost per kilogram by dividing the cheapest price by the expendable payload. Those numbers aren't in the same part of the table. Now, there are a number of ways you can get a more accurate estimate of the payload of the reusable configuration. If you'd like to dive into the weeds on this, I'll encourage you to take a picture of this QR code in the corner. It will take you to a 17-minute video that covers how you can more accurately estimate the cost per kilogram of a Falcon 9 and Falcon Heavy. When you calculate the payload correctly, it turns out that launch costs might be dropping at a rate of about 2x every 30 years, which is this bottom curve here. But these are correct calculations or better calculations of the cost of the Falcon 9 launch. So, NASA says the prices are actually going up over time. This graph says they're going down slightly over time, but what's clear is that they're not dropping fast. They're dropping slowly, if anything. Incidentally, Falcon Heavy, if you think about it, is probably more expensive than Falcon 9. Now, this is partly because they don't reuse the core stage of the Falcon Heavy. But think about it, if Falcon Heavy really was cheaper than Falcon 9, then why wouldn't SpaceX use it to launch their Starlink satellites? It doesn't make sense. So it's probably more expensive. And there are actually some older reports that state that it actually is about the same price or more expensive than Falcon 9. All right, but there's an even more significant contribution to this overall theme of the costs. And I spoke about this last year. And this, by the way, this QR code will take you to last year's presentation. The even more significant factor is that the cost is proportional to the exponent of the mission delta V, just like the mass ratio is proportional to the exponent of delta V. Now, don't forget this is a log-log graph. So, for example, the Mars sample return mission here is 6 orders of magnitude more expensive than just going to orbit on a cost per kilogram of useful payload basis. So the JPL mission designers assigned to the Mars sample return didn't suddenly just become 6 orders of magnitude less efficient overnight. This is more of a techno-economic harsh reality of rocket-powered spaceflight. There are 2 main reasons why, at present, the geopolitical policy wonks have no fear of missing out on the space settlement bandwagon. They know the truth about launch costs being more or less flat, and they also know that when the serious engineers at NASA come up with a plan for how, for example, to go to Mars, it is always way too expensive with rockets. Okay, I don't have time today to talk about all the alternatives to rockets, but I will talk briefly about what I believe is the most promising class of alternatives, which are electromagnetic launch, or EML technologies, also known as mass drivers or ground launch assist. First, I presented at the EML conference in Amsterdam last year. There were lots of attendees from all around the world. Most of the work is being funded by defense spending, railguns, for example, and electromagnetic aircraft launch systems like they have on the Ford aircraft carrier. Some seems to be funded by fusion research. Second, there are related fields such as magnetically levitated trains, high temperature superconductors, pulse power, and magnetic bearings that have real world applications right now, which are driving some of the relevant technologies forward. But despite there being lots of progress in small scale applications of electromagnetic launch, we still haven't attempted to build a launcher that can launch things into space. And there are a number of wrong reasons for this, which I'll cover first. But first, let's take a quick look at what a scaled-up launcher might look like. To build this thing, we need a factory on this island, which will construct and extrude this part of the launch tube. It's quite long. It's like 700 kilometers long. There's also going to be a tunnel boring machine that will tunnel through the island to make a curving upwards ramp. And finally, there's this component up here, which is an elevated evacuated tube. The spacecraft enters through this airlock. This is sped up so that it won't take too long to watch launch. But the idea is the spacecraft is accelerating the tube, which is underwater, until it gets to the island, where it enters into the tunnel, which is basically the ramp. And it ramps upwards and then travels through this elevated evacuated tube. And when it gets into the upper atmosphere, it fires its rocket to push itself the rest of the way through space. This is an idea I actually presented on last year, but I want to kind of go into more in depth on the reasons why this technology actually makes sense. So here are some of the reasons why, or the reasons people have come up with to say why this won't work. And we already covered reusable rockets have already solved the problem. So let's continue with accelerations are too great. By the way, accelerations are too great is a legitimate reason why a funded technology like spin launch can never be human rated, obviously. But linear launchers live by different rules than spinning launchers. If you took high school physics, I'm sure you'll remember that velocity squared equals 2ax. If you fix the velocity, then you can make a graph to show how long the launcher needs to be for a given acceleration, which is this graph here. So you can always reduce the acceleration to ensure the crew will survive, but reducing the acceleration makes the launcher longer. Also, the more acceleration the passengers can tolerate, the less time they need to tolerate it for. Basic physics. Now, this chart's a bit hard to follow. It comes from a 1958 Air Force report. But what they figured out through placing idealistic young men in centrifuges is that if you immerse someone in water, then they can handle G-forces of around 7 to 12 Gs for time periods of about 4 to 7 minutes. So I imagine we could human rate a high G launcher by installing sort of rotating water beds, which I've sort of drawn here. And these water beds would orient in the direction of the acceleration so that the crew would feel less G's, obviously, and the ramp, they would point upwards. So that's acceleration is too great. Next, is the whole thing too long? Well, if you think that a launcher on the order of 1,000 kilometers is too long, then this chart might help put things in perspective. Keep in mind that this is a log scale on the bottom. The orange bar represents our 1,000 kilometer long hypothetical launch system. The bars above it are other human achievements. The Romans built paved roads, which in total were 150 times longer than our launcher. The troops in World War I dug trenches that were 56 times longer than our launcher by hand. And even the Great Wall of China is 21 times longer than this launcher. So perhaps a good way to think about it is if we divide the 1,000 kilometer length by the US population, then the per person length of the launcher is just 2.9 millimeters. Also, 1,000 kilometers is a value that's in line with what major suppliers of large diameter concrete pipe or steel pipe can produce in a year. So it does seem long, but it's actually not that long. All right, next is the tunnel too long? Well, the launcher I just showed you has a skyward curving ramp at the end, which can be made by boring a tunnel through a mountain. Such a tunnel would be about 75 kilometers long and a lot smaller in diameter than your typical highway tunnel. To put that in perspective, CERN currently has over 60 kilometers of tunnels, and CERN's future circular collider, the FCC, has a planned circumference of 91 kilometers, so it's in the same scale as that project. And the next question is the evacuated tube too hard? Well, this concern, I think, comes from the Hyperloop debunker community. their concerns get mixed together to create an overall vacuum tubes are a bad idea or narrative. For example, there's a concern about the Hyperloop pods springing a leak and everyone inside suffocating in the vacuum of the tube. But this is not exactly a new risk for spaceflight. I think that perhaps a more reasonable concern is whether you can afford to get people in and out of the evacuated tube for a small fraction of the price of their ticket. This is a concern that doesn't really rule out evacuated tubes for space launch, though, since the ticket price for space launch is so much higher. Now, the technical viability of long evacuated tubes has been well established by the work at LIGO, LIGO observatories. Each observatory has 8 kilometers of evacuated beam tubes. These are shown up here. They've been able to maintain a vacuum inside these tubes of around 2 trillionths of an atmosphere for over 25 years. That's 0.000000202 pascals. Now, our requirement is 5 pascals, which is something like 7 orders of magnitude less stringent than their requirement. But the LIGO observatories combined are only about 16 kilometers long. Our accelerator needs the ramp to be a tube that's about 861 kilometers long altogether. So the accelerator plus the ramp is 861 kilometers. So the question we need to consider is whether it's possible to spiral weld the tube 53 times longer than what they did for LIGO, and then also about 5 times wider. So on the scale of what we need for the launcher, we currently use spiral welding technology to produce the towers for wind turbines. The diameter of these tubes is similar to what we need for a launcher, and there are roughly 50,000 kilometers of wind turbines installed in the world already today. So the launcher only requires about 2% more. The next reason is this reverse reentry idea is the flight regime is too difficult. And the Air Force funded a study that established that it was possible to launch from a high-altitude aircraft into space with a railgun. But I thought it might be more fun to address this particular concern in a less technical way. Arthur C. Clarke once said, "Every revolutionary idea seems to invoke 3 stages of reaction." They may be summed up by the phrases, "It's completely impossible," "It's possible, but it's not worth doing," "I said it was a good idea all along." So let's see if there's any truth to what Arthur says. Stage 1, it's completely impossible. Well, Elon Musk tweeted back in 2015 that anything launched by a railgun would explode upon exiting the barrel in our dense atmosphere. However, this is clearly not true. In fact, this projectile that the Navy launched out of a railgun a year earlier did not explode even after passing through a couple of thick sheets of steel. Here's a picture of it after it goes to the first sheet of steel. You can see it's pretty much still intact. So, not true. But, a little later, stage 2 came along. It's possible, but it's not worth doing. So on November 10th, 2021, Elon tweeted, "As described in The Moon is a Harsh Mistress," great book, "a linear accelerator would be great for the moon. Earth's gravity is too high and atmosphere too dense for accelerators to be a good solution versus reusable boosters, in my opinion." Sounds a bit like it's possible, but not worth doing. And stage 3, I said it was a good idea all along. Well, we're not quite there yet for this concept, but anyone familiar with Hyperloop will be aware that Elon has at least said all along that a long evacuated tube at least is a good idea. The next is the evacuated tube too high or too hard? I'd like to show you some video clips to prep you to believe in this idea of an elevated evacuated tube. And next one is this one. These are light show drones flying information with extreme precision. So you can see how precisely they're flying. It's really interesting. And finally, we have Ingenuity, which is a drone that NASA designed to fly in the rarefied atmosphere of Mars. And by the way, it's a very efficient flyer, turns out. Now, if you drop on these heritage technologies, as we call them, and combine them, you can build this. A long evacuated tube supported by lift fans. These fans receive power from a power plant on the ground through a high voltage cable. And we've done the work to cost this out, figure out the requirements for powering it. And it looks to us to be completely technically and economically feasible. Now, this last reason, it's often brought up when someone asks, so the last reason, by the way, is still has a rocket. It's cheaper to make the rocket part bigger. This is often brought up when somebody asks, why don't we launch from the top of a mountain, or why don't we launch from a train? It's probably a valid concern or counter for modest ideas that have small gains. But I'm going to skip this one for now, as there's a slide coming up that I think will adequately cover this concern. Okay, what this slide is saying is the real reason earlier EML concepts failed is that the cost of hardware that conditions the power, and I know this is a very complicated slide, but it's saying that the cost of the switches and the power conditioning hardware that turn on and off to propel the vehicle is incredibly expensive. It's not that the individual parts are particularly expensive, it's just that you need an awful lot of them. And you need these kinds of switches, the kinds of switches that can handle the power output of the Hoover Dam times about 2 million. And that's a lot of power switching capacity. And it's what's known in the trade as the switching problem. Now, it's a bit of a complex topic, but if you'd like to learn more, there is some information on the StarTram wiki page in the challenges section. And I'd be happy to share a link to a paper that's in peer review right now that covers this in more detail. I need to explain why or how a technology called variable pitch screw launch solves the switching problem that has prevented earlier electromagnetic launch concepts from scaling up to space launch. So the way that variable pitch screw launch works is that instead of converting electricity to kinetic energy on the fly, the way other EML concepts do, it instead does that conversion between launches. So every screw and the flywheels inside the screws are accelerated gradually in parallel over a period of around 40 minutes. And this approach requires millions of times less power conditioning hardware. Then the momentum of those screws and the flywheels is transferred rapidly to this component called an adaptive nut. The adaptive nut is essentially a magnetic worm gear. It's like the traveling component of a magnetic worm gear. It transfers momentum through the worm gear, and that transfer doesn't result in high capital costs. It's a cross-section of a screw flight, which is part of a design study we did. Here we're estimating that we should be able to get the screw flights to move at about 800 meters per second. As we want this launcher to launch vehicles at about 11,123 meters per second in order to send vehicles to Mars, the maximum pitch we need at the end of the launcher will be about 14 to 1. So that gives you an idea what the slope of the screw thread is. We figured out the cost of VPSL, or variable pitch screw launch, scales with the square of the exit velocity. If you recall, we showed earlier that the cost of rockets scales with the exponent of delta V. It's a big difference there. So the cost savings you get will depend on the delta V you need for your mission. As you can see, it's significant for higher delta V emissions. So this curve here is what's representing the V squared cost increase for a variable pitch screw launch. And this curve represents the rocket's cost curve, the exponential curve. And you can see as your delta V goes up, the savings become quite significant, up to 1,000. And this is an enormous savings benefit that's driven by fundamental physics. It's not the kind of thing you can get a similar benefit from by just making the rocket part a little bit bigger, to address my earlier point. So we can cross this last wrong reason off our list. VPSL technology is relatively simple to manufacture from basic materials like steel and aluminum, and these are materials we should be able to get or source from the Moon and Mars. On the Moon and Mars, you don't need the elevated evacuated tube. In fact, on the Moon, the tube would be more like, the main tube would be more like a dust cover than keeping the vacuum out, because there's already vacuum on the Moon. And on Mars, the pressure is very low, so you just need a very thin tube to keep the air out of that tube. Also on Mars, you'll find some really nice tall mountains like Olympus Mons, which would be great for making the ramp. The best part is it doesn't take a lot of money to launch spacecraft with VPSL technology. It's a very efficient technology, whereas it does take a lot of money, or a lot of energy, I should say, to synthesize enough rocket fuel to make the return trip from Mars to Earth. So VPSL is a technology that can provide an affordable round-trip transportation system between Earth and the Moon, and between Earth and Mars. So settlers will be able to come back, which I think is probably a pretty important prerequisite for being willing to go there in the first place. We also think the suborbital version of VPSL might partner well with the concept that Roger will be presenting on later at 11 a.m. So where do you come in? Well, what I talked about today is covered in a 22-page peer-reviewed paper. If any of this intrigues you and you want to dive into the weeds, I'd encourage you to get that paper and read it. Please see me afterwards if you'd like an electronic copy. There's also a great blog by John Chaucy, which you can find here. and a video called Mass Drivers versus Rockets by Isaac Arthur, who's here, by the way. And there's a lot of other videos that I presented at previous conferences, other conferences, and I put stars on the ones that are most relevant to the space launch concept. There's also a page with several links to papers if you're more of a reader. There's lots of ways you can contribute, but I think I'm running out of time. I realized we didn't spend nearly enough time on explaining how variable pitch screw launch technology works and why it breaks through the earlier barriers, technical and economic barriers. But what I'd really like you to take away from this presentation is the idea that I put forth at the start. And that is that there's real value associated with taking the time to dive in, figure out for yourself if what I'm saying about launch infrastructure is true. Because if you reach the same conclusions that I have, and if you convince one or two more people to go through the same process, then eventually we'll get to the point where expansionist powers will see the moon and Mars as places that are almost within their grasp, and also places that they would not want to miss out on. And hopefully, gradually, these powers will begin to turn their attention away from the zero-sum conflicts that we're seeing happening here on Earth, or if not happening, then perhaps brewing, and focus more towards space. And this could lead to trillions of dollars being redirected towards projects that are far more constructive for our civilization, and hopefully also avoid a lot of needless death and life-altering injuries happening because of zero-sum political conflicts that are happening here on Earth. Here are codes to the presentation if you want to get a copy. Chris, you're up next. Got a question?
Yeah, I have a question. So if you didn't have biologicals on board, no humans or specimens?
Yeah, there's definitely people.
You need the same length now.
No, you could make it shorter and cheaper if you just launch payloads like higher Gs.
So how much shorter do you think would be then?
Well, that comes down to that curve that I showed earlier. This technology is really probably pushing it to go much beyond 10 Gs of acceleration. But you probably could go faster than 10 Gs of acceleration, but it's not like a gun so much as it's pulling something along with magnets. So I think this technology, I haven't explored it, but I don't think it's a great idea to try to make it do like 100 Gs of acceleration or anything like that.
It seems gentle on equipment than spin launch would be.
Oh yeah, definitely, because spin launch is like hundreds of thousands or tens of thousands of Gs. Yeah, a lot. Yeah.
What's the mass of the projectile?
Yeah, so there's 2 or 3 masses. There's the dry mass, which, oh boy, I think it was like 17 tons. There's the wet mass when it's launched, which I think was 28, if I recall correctly. It burns a little bit of fuel on the way up,
Right.
so you get kind of a new wet mass when you're on the way to Mars, and that is an important value because of you can use that mass for shielding. And we have a strategy of actually amalgamating a fleet of these ships into a clump so that have more radiation protection on the insides. But these are all numbers that you can play with. We have a full digital twin and cost model, and if you play with these numbers, you can change them around to something else if you want. Just changes the price. Yes?
Maybe come up with a cost estimate to build.
Yeah, so the current cost estimate is $35 billion for a mission that would put like a 20-year-long space program that would maintain a base on Mars, which is a lot cheaper than what Artemis is costing now just to go to the moon. Now, we're still playing with some interesting numbers. Like if you recycle the entire thing at the end, you can get a lot of the money back, so that it could actually be less than 35 billion. But it's around 35 billion. I think I'm out of time. But like I said, the last speaker did cancel. So if you stick around to the end, I will have some time for more questions at that point, and we can dive into some topics if you like. Chris, next, come up and speak.